All right. Thank you to everyone who got up so early this beautiful Friday morning after the fabulous party we had last night. And for everyone who was attending virtually, I'm sorry you missed out on it, but I'm sure there's plenty of footage and video and all of this kind of stuff from that, because it was pretty fun, and I'm sure people are a little bleary-eyed. So thank you to those hardcore native developers who came out here. And let's see if this works. I get lucky. All right. So, NDK performance in our world. How many people here are NDK developers? All right, this is good. This is good. I'm excited to see so many people out there who are doing this. This is a labor of love for me, this talk, so I'm really glad you guys are here. And, there's a lot of Android development where you get to just blissfully ignore a lot of what's going on in the operating system. I take the blue pill. You don't really need to know what's going on and how the matrix is formed. You just get to go and code in a nice, beautiful environment in managed code. But today we're actually going to take the red pill. We're going to get a little bit inside how things work, and I hope it's fun. And whether or not it's useful or not, you can tell me, but at least hopefully we'll all learn something from this. And of course, when I'm talking about native code, I'm referring specifically to unmanaged code that's not using the Android runtime. And one of the primary reasons that people end up creating this code is that they already have a bunch of working C code. When you have a lot of code that works, you create new code, you just create bugs. No one wants to do that. Now, of course, your legacy code might not include support for really, awesome multi-processing, or might have, not have support for neon intrinsic. So even though it's awesome that you have this legacy code, you're not always guaranteed to get the best performance with it. That being said, performance. There's a lot of people who write NDK code for performance reasons. How many people are doing it for performance reasons out there? How about cross-platform compatibility? Let me just have a show of hands. Okay, so it's about the same. And a lot of that means to get the best performance, though, you need to know about things like the number of types of cores, thermals in the design. Like, there's a lot of different variables to actually making sure you have, the best performance. But oftentimes, native code is your only option. And of course, reach, you want to be able to hit multiple platforms. And C++ is just getting better and better at isolating the operating system for you, which is awesome. And finally, the NDK has a few capabilities that aren't yet available inside of the runtime. Now, what I'm excited about is that actually, if you look, when I wrote this talk, you had to actually, to get low latency audio, you had to use OpenSL. And if you want to get the absolute lowest latency audio, you still need to use that. But I'm really excited that in Android N, we actually are now allowing people to use Java to get pretty darn good latency on their devices. And of course, it's the only way to access Vulkan, the graphics API right now. And that just makes a lot of sense. If you've ever seen how verbose Vulkan is, you definitely don't want to be making that many JNI calls if you don't have to. Not that it doesn't work. So, this is probably a review for you, a lot of you, since you're all NDK people. What exactly is it? It's a combination of tools and headers that allow Android development. All applications are eventually tied to managed code running in the Android runtime. And the Android framework itself is written largely in managed code. Your libraries are ultimately loaded into this framework, typically from within Java code. And they all get to talk to a stable application binary interface, which then, of course, talks to the native system libraries. And this is important, because a lot of people are like, well, why can't I just use all those other libraries that are there? And people have done this, and that's why compatibility breaks. And we're actually, one of the things that we've added to N is if you actually try to use any of those internal libraries, they will not work anymore. We actually have separate link spaces. So there's good and bad news to this. The bad news is you're actually going to have to put things like libpng into your app. The good news is when you put them into your app, you are guaranteed to get your version of libpng on Android N and above. While on previous versions of Android, that was not always the case. So I think, in a way, it solves a lot of problems. All right. So it's grown over the years. And it started off in Cupcake, and we added media features and gaming features and the ability to do fully native applications, lots of cool stuff. Recently, however, we've actually gone even further. We've actually put RenderScript finally into the NDK, so there are bindings for that. We've continued to expand graphics with Vulkan, and we've added a couple of really interesting ones in the latest versions of the NDK. We've added Trace, Choreographer, and Multi-Network, and at least I'm going to talk a little bit about Trace and Choreographer in this one. So in addition, the NDK toolchain, which is separate from platform releases, has had its own set of 12 major releases and many minor releases. 12 just came out this week if you haven't seen it. And here are some of the highlights. We added STL pretty early on, and then we fixed it. We added more platforms like x86 and MIPS. We added the Clang compiler in 8C. And the misunderstood ARM7 FP and 9D, which we are actually taking out of NDK level 12. So 64-bit in 10, and in 11 we finally transitioned to Clang as our primary compiler. We've actually deprecated the use of GCC. In the middle there we moved to LLDB as our primary debugger. But again, this talk isn't just about the NDK, it's also about ART. So what I did was I was really curious, like ART is a totally different beast than our previous runtime. So how does it affect the NDK? And so what I did is I went through the perf JNI article. I mean, probably everyone's read this perf JNI article, right? Like, yeah, like, or if you haven't, you really should. Because the real question I wanted to know was, do these tips actually make sense in an ART world? And so we're gonna keep a scorecard for both ART and Dalvik for each one of these tips. And so let's go through them. And we're going to benchmark these. I actually benchmark these with Google Caliper, which is pretty cool. It's actually what we use inside of our CTS tests for all of our benchmarking. So it's about as good as you can get. We use it a lot internally with Google for doing all sorts of benchmarking. So if you ever want to set it up, it's actually pretty cool. You'll learn a little bit about Android just setting this thing up. Hopefully we'll make it more user-friendly at some point in the future. And so the basics. When you're using JNI to reference managed objects, you're actually taking advantage of reflection. And named, of course, because it describes the ability for code to inspect itself at runtime. Now, to access a class field, we take the object reference for the class and use reflection to request the field ID by name. Okay, and from our developer training, here's what it says. It is important to cache class references, field IDs, and method IDs because they are guaranteed valid until the class is unloaded. And that rarely happens, and it's really easy to catch if it does. So let's look at our first performance suggestion and how it holds up under ART. So a nice way to cache these IDs, which nicely solves the unload problem, is just to put it in the static initializer. So there you go, you call like this one native init. Inside of that, you get all of your field IDs. So as you see, I'm making a native call inside of my static initializer, which is kind of slick, right after loading the library. And now those IDs are good forever. So it's really nice if the class gets unloaded, the static library initializer will get called again. And here's how it benchmarks. And it turns out, and this is the Nexus 5 running KitKat and Marshmallow. But as we can see, both get field ID and get in field are actually slower in ART. In other words, the advice to cache field and method IDs is actually more important in the world of ART than it was in the world of Dalvik. And we'll see a trend here. And the difference in the cost of get in field is a little surprising. Both runtimes actually change the state of the internal thread. And that's actually what costs a bit of performance here, although ART actually clarifies what it's doing with scoped object access rather than scoped JNI thread state. And what we're seeing is a couple of things. One is that ART is pretty complicated by comparison to Dalvik, and it's got a lot more going on. The garbage collector is much more sophisticated. It's much higher performance. And the other thing is it's just being really defensive. There were definitely times in Dalvik where you could cause it to deadlock. And it's very, very difficult to make ART do that. So that's the beautiful thing about all this work they did, but it does cost us a little in actual performance. So this is something to note. Also, I love this use of the preprocessor to prevent all this duplicated code. Okay, as far as caching field method IDs go, it's a big win on Dalvik. It's even a bigger win on ART. So let's look at our second performance suggestion, and we'll see how it holds up. If possible, it is usually faster to operate with UTF-16 strings. Android does usually not require a copy and get string chars, whereas get blah, blah, blah. Okay, I don't have to read that to you. Basically, it makes sense. If we don't have to copy strings, it's going to be faster, right? So here are the two calls that get a string. You can either get the UCS string, which is a 16-bit standard format for the managed side of things, and UTF, which is, of course, what a lot of our native code expects. And we would expect, and since there's no conversion going on, that actually the UTF would outperform the UCS. Okay, so let's take a look at how this actually benchmarks. And this was a little surprising to me because this was a short 15-character string. And it turns out that it was actually faster to send the 8-bit decoded string across instead of the 16-bit string on ART. On Dalvik, you can see it actually benches the way you'd kind of expect it to. But even then, it's very, very close. And it was a little bit of a surprise. And the reason, and so I was like, okay, I've got to understand why this is happening. So basically, I was like, let's first of all try a longer string and see if it actually behaves correctly. So with a longer string, we actually see, yes, this actually benches out the way we expect, but it's a little surprising. So let's look at the code and see what actually is going on. So you can see inside of art, there's this line called isMovableObject. And it sometimes gets to return a copy and sometimes returns the original string. And isMovableObject is actually kind of an expensive call. So what ends up happening is that this is actually, it's a for loop inside of here that goes inside this fine continuous space from object, and that's actually what takes the time. So what it really ultimately on art, for a lot of normal string sizes, you might actually be better just sending them the UTF-8 today. Now, of course, this is all subject to change, and maybe they'll watch this and be like, oh God, we've got to fix that. But at least today, that it doesn't matter all that much, as it turns out. So that was a little bit surprising. And again, this is a micro benchmark, so it certainly is going to help prevent garbage. Is this working? All right. Fortunately for all you people on the live stream, I've got a microphone. So on our JNI tips scorecard, it's probably a decent idea to do it on both, but it's definitely better on Dalvik. Finally, let's look at one more tip here. And this is actually me paraphrasing because I couldn't come up with a quote that was even close to being good enough. This is actually a very, very good thing that I would actually paraphrase because this is important because you want to reduce JNI overhead, and actually using region calls to copy data, if you're going to end up copying it in the finality, it actually saves you quite a bit of performance. So here are the two native functions that copy data from string into a buffer. One of them does it using kind of the old school way of doing get, copy, and release, and the other one does it using get string region, which is all done at once, which is cool. You're eliminating some JNI calls. And as you would expect, and the other thing I was going to point out here is that I actually passed the length of the string in as well. Now I could, of course, just pass the object from the runtime and query it, but obviously that would be another JNI call. That'd be a huge waste of time, and it turns out that it's 20 to 30 times faster just to pass an additional parameter rather than making another JNI call. So as a general rule, you're going to always want to have more parameters calling into your native functions if you can possibly avoid ever making a call back into the runtime. Okay, so here's how it actually benchmarks for copying string data, and once again, this is kind of what we'd expect. That the get string region is extremely close actually between the two VMs on the same hardware, and get string cares is definitely slower than both of them. So region is definitely a good one. We'll put that on our scorecard. So sharing structured data between managed and unmanaged code in the fastest possible way isn't as easy as sharing a soft drink. You basically have two options. You've either used arrays or direct byte buffers. And it really comes down to your use case. If arrays are useful if you're primarily going to be accessing the data from managed code. But here's what our tips say about direct byte buffers. Okay, this seems like a rather uncommitted statement. Like, you think we could do better than this, okay? Is it actually slow? Like on both of our runtimes on a real device? Well, this is why I was like, I've got to benchmark this one too. And actually, it's not terribly surprising, but we see about 2 times the raw JNI cost in order to get the direct buffer address access rather than just using the standard stuff that's built into the runtime. But you notice something really interesting here and about this one, and that if we actually go to read back from the byte buffer, it's actually like 3 times as expensive to read from Dalvik compared to using art. And like this makes no sense. Like why? Like we've seen in every other call, we've seen that Dalvik does this much faster than art. So what's going on here? Let's take a look at what's going on actually inside the code. So basically, here's what this looks like. As you'd expect, this is our byte buffer, direct byte buffer. We can see that a regular byte buffer is actually backed by a Java array, while the direct buffer is backed by a memory block. And so far, that's exactly what we'd expect. And here's how we start actually reading an integer. We can already see that direct byte buffer has an additional level of indirection. And based on the profiling I've done, that probably costs us about 5 nanoseconds. And now we're somewhere. Here's our byte array implementation and our memory block implementation, both conveniently in the same class. And our memory block version actually uses JNI. So that explains why direct is so much slower. It's actually doing a full JNI call just to access this memory. But why is ART so much faster? Well, here's what that native code calls into, but it still doesn't tell us why ART is faster. The real magic actually happens where the JNI function is declared. Because JNI overhead is pretty high, the runtime actually kind of shortcuts it into a fast mode in certain cases. So inside of ART's native code, we declare the JNI call with an exclamation point to make it clear that this is a potentially dangerous function, and now the thread gets to stay in running mode without having to switch to native. So looking back at our graph, our direct call is about half the speed of our byte buffer call. And this is partially because the version of the runtime is actually using another trick. It's really an inline intrinsic. So we're never going to get the kind of performance out of our native call as we will, even without most of the overhead compared to what's going on inside the runtime. And partially because we have a little bit of overhead even in this kind of fast mode. And this is about 60 nanoseconds of overhead on a Nexus 5. So it's not huge. I mean, these are tiny, tiny amounts. You have to remember that almost every single call you make in Android ends up going through one of these eventually. So the question is there anything we can do to avoid having to make a call into JNI for each int we want to read? And it turns out there is. We can copy the entire array at once and then get the int individually. And now we're going to do some pretty expensive stuff here, so it only makes sense if you're going to be reading a lot of structured data from the byte buffer. As always, you'll want to profile just to make sure. But once again, you can see that this is pretty awesome in terms of ART. All right, so that was the really, really scientific part where I did lots of benchmarking. Let's get into actually doing some fun stuff that's maybe more practical. So this slide mostly demonstrates why I'm not a design advocate. But there are lots of choices to be made when using the NDK, as well as some updates I'd like to highlight. So we have a couple of samples here, and I wanted to show you them. Let's see, on this phone I have up here, and this is actually running the NDeveloper preview. And there is a really cool NDK sample we have up here called More Teapots. And you can see in normal mode, it runs at 60 frames per second. This thing uses geometry instancing to get actually pretty decent performance running even with fairly a lot of teapots flying around, basically. And if we switch over to the laptop, you can see I've actually taken a systrace of this. Now, how many people here have actually used systrace? I want to see a show of hands. Because systrace is like my favorite tool ever, almost. It is pretty awesome, and it's kind of hard to understand completely what's going on when you're just looking at it here. So basically, you can see that there's this inside of my More Teapots application. I've got thread 9491, and inside of that, I can see EGL swap buffers with damaged KHR and a Q buffer. And then if we look also inside of our Surface Flinger, we can actually see that there's a thread that's tied to that as well that's responsible for updating that surface. But we can do a lot better. And let me show you a little bit of what we can do. Okay, back to the slides for a second. So, I did want to go over a few more things here, but I'll do that later. Okay, so what we can do, start off, is let's get rid of that ugly name. We can actually name our threads. In this case, the code is actually attaching to the runtime. And so you can see here that we actually are using this attach current thread with attach args. And if we do that, and let's see if we can switch back to, let me see, back to the laptop. And I'll show you kind of two things here. One is that I've actually added something called too many teapots. So this is like, instead of 512, which the regular demo has, we're now looking at one that's rendering 4,096 teapots, which is actually way too much for this poor, sad Nexus XP to do. And you'll see a couple of things interesting. One is that we now see that CPU 4 here is actually active. And that's really, really bad. Because CPU 4, it turns out, is one of the high-performance CPUs that just absolutely will cause the device to thermally throttle relatively quickly, especially if someone has it inside a nice insulating case, which, of course, a lot of people do. In fact, I did this with and without cases, and I got about 10% better frame rates once I took it out of a case, just to give you an idea of how these things actually matter. But the really cool thing is you can see if we go down here, it should be here, maybe. If it's not in this one, it'll be in the next one. This is supposed to have a named thread. Oh, this is the challenge with getting sys traces. Sometimes I miss things, but in any case, this will actually show the thread named, I swear. Okay, let me show you a couple of other things on the actual device itself. So this is the too many teapots demo. As you can see, it's running at about 12 frames a second, which is really not very good. But let's say we absolutely wanted to put 4,096 highly occluding teapots into our game, running at some reasonable resolution. Okay, how would we actually use what's built into the NDK to help us with that? So we can switch back to the slides. I'll talk a little bit about that and what we can do. First of all, we want to know what's going on with performance. So one of the cool things we've actually done is we've actually created a native trace API, and this has actually been in the platform ever since M. So we've always had the begin and end section, well, not always, we've had begin and end section for several versions, which allows you to actually annotate these sys traces, but now we actually have a native API to do it for you. So we can actually see not just like the KHR swap buffers thing, but actually individual sections of what's going on in our engine, which is really, really awesome. And you just do a trace begin section, a trace end section. It's pretty lightweight. It's a lot lighter weight than doing a log statement. And you'll actually see all of these things show up in the graph really, really nicely. Now, one of the things we can do really, really easily is to reduce the size of our render target. Now, what's cool is that actually using the asset manager APIs that are built into the NDK, we can actually get the density of the screen. And that's useful because obviously we might want to say our application doesn't need to render in anything higher density than HDPI, but that's nice because it still actually preserves the screen size. It means that we're actually really truly giving the user a decent experience by using density as our target. So let's switch back to the phone here, and I can show off the first thing we can do here. So this is just scaling the target. Obviously, that's not a very good user experience here, but that's actually scaling it based on density. So I'm actually now rendering the screen at old school HDPI. Just by using the density metric there to scale, but obviously that's not very good, but we can do something better. And as you can see, we're getting a good performance gain. We're about 25 frames a second here. However, we can actually make it even faster and actually make it a better user experience all at the same time. And by taking advantage of the compositing engine inside of Surface Slinger to do some of the work for us and actually save some memory bandwidth in the process. So we can actually, let's see, yeah, let me switch back to the slide here for one moment. Okay, so this is what we actually do. So in addition, so once we've gotten that we know the ratio that we want, all we have to do is call a native window, get the right format, because we don't want to change the format of our native window when we do this, and then we can call set buffers geometry. And this is pretty cool, because what it'll actually do for us is it'll automatically scale that render target for us and make things a lot happier and a lot more friendly. And actually, when you're looking at this on the device, unless you're looking carefully, it's really, really difficult to notice what's going on here. So we can switch back to the phone, and you can see what I'm talking about. So now this is, once again, this is using the internal compositing engine to actually scale things up. And you see we're actually doing better than we were even rendering in just a little corner of the window because it's actually using less fill. And the other thing that's really cool about this is the FPS is actually being rendered using a pop-up window. And that pop-up window is actually running at the full device resolution. So that text that you're seeing there is actually rendered at the super high DPI stuff, and only the background is actually being rendered at our lower resolution. And the compositing engine on a device like this can do enough windows that we're actually getting the benefit of that. So we have a HUD running at really high res, and we have a background running at a lower res, and you can barely tell because our eyes seeing characters with a bunch of jaggies is really noticeable to us, but seeing a background that's a little lower resolution, not so bad. So this is actually a cool trick. I don't think I've ever seen anyone use this in a shipping app, but it can be done and it works pretty well. The one trick about this one is it really helps to be in immersive mode when you're doing this because the pull downs for the notification and for the system buttons at the bottom actually also take windows. So by going into immersive mode, you actually free the system up to have more windows to use for your app in the compositor. Okay, so we can actually go back to the slides now. Okay, So another thing we could do is actually say, let's try to cap the frame rate. And we actually have added an API called Choreographer, and Choreographer is great. It actually gives you a callback whenever there's vsync coming in. And up until N, it was only available inside of managed code, but inside of N, we're now opening it up for use in all of your code inside native code. And there's a great example of this, actually. But let me actually show you what that looks like. Well, so we can switch back to the device here. Where is this one called? Oh, maybe I don't have it on that screen. Yeah, there we are. And so now this is actually using Choreographer to lock things as close to 30 frames a second as possible. And you can see there it's like 28, 29. We're still getting some jank, and you can see that it's probably running on the thread, so we're overheating pretty quickly there. But that's another great thing you can do. And what's awesome about Choreographer is a lot of people are like, their app or game doesn't need to run at 60 frames per second, and they'd much rather save the user battery life, not have the phone overheat in their hand. You know, users actually respond on comments are like, all right, I played this game and I was burning up and I had no battery left an hour later. And one easy thing to do is say, you could even make a slider saying what are the frames, do you want to limit the frames per second of your game? And for a lot of games, that actually is huge. And Choreographer allows you to do that in an extremely, extremely power efficient way. And what we're actually doing in the code, we can switch back to the slides here, is basically we're getting a frame callback, and then we're simply every other frame callback we're swapping. So it's pretty straightforward. This is not the most intelligent way of doing this, because you will get jitter. If we're not actually able to render at 30 frames per second, this is kind of awful. But as long as we're actually able to do this, this actually works pretty well. And it's actually not that hard to make it more complicated. This is just the sample that we ended up writing. What's cool is if you do go to that QR code, that sample is live today, and it's cool. It actually uses Choreographer if you're on the latest version of Android. It uses EGL extensions on a couple of older versions. It actually goes down to the Java version of the API on earlier versions. So you actually can see how to do it all the way back to, I think, 16 or something like that, which is pretty nice. So the sample is cool. It's a little complicated. And it's not using more teapots. It's just a single teapot. All right, so I showed you that. And so there we are. We got a little bit of performance clawed back. We're getting around 30 frames per second now when we're not overheating under the wolf vision here. And this is even better than we did with reducing the render target. And we haven't had to add a single non-native call to do any of this. Mind you, every single thing that you're watching here has been entirely inside of the NDK, which I'm very pleased about. And I'm sure that our developers are too. Now let me show you one other little thing that we can do, and that you might want to do, and why you might not want to do that on N. So how many of you have heard about what we've done with sustained performance mode? So sustained performance mode is a feature mostly intended for things like VR that really, really require you don't want to drop frames, you don't want the device to overheat. And so basically what they do is they actually try to put the device in a mode where it's never going to overheat. Now the problem is that at that rate, under the conditions they test on, you're not going to get the highest performance. So what I've done is I've actually taken a version of the app that actually uses that API. This has got all the other optimizations I put in other than the Choreographer one because it just gets too horrible. And you can see we're now getting sustained performance. It will never overheat running this. You can run this for hours, but we're about 15 frames a second. So you do give up a lot. But if you absolutely need sustained performance, you can do that, especially if you're doing things like pro audio where you're really, really worried about glitching. This actually does pretty well. So that's another option for you. Again, it's just a new window call. This is the first actual call through JNI that I've had to make in all of this. But as you can see, you lose a lot of performance. You really do have to make a call there. Okay, we can go back to the deck now. All right. So there are a lot of big choices to also make when using the NDK. Do you use Clang or GCC? Do you use hard FP, 64-bit? And I wasn't sure, so I went and did more benchmarking. This was like a bear to prepare for this thing. So let's talk about performance. And if you look at Clang versus GCC in 32-bit mode, it's pretty much the same. it's going to be, and sometimes it's exactly the same. Literally the Whetstone number is identical between these two, and they're within 1% or so in the other two, which is kind of what we expect. And if you actually run your code and run benchmarks on it and you see anything different, report it to our compiler team. There's actually a place where you can file issues on our NDK site. Let us know, because the team is really, really very, very aggressive about trying to make the compiler perform well. In 64-bit world, it's actually also just as close. GCC sometimes outperforms Clang, Clang sometimes outperforms GCC, but it is completely not noticeable. These are very competitive compilers. However, when we look at build times, and this is our Zushi application, and this is kind of crazy, because Zushi actually has tons of assets that get built along with it. So, and I didn't even pull them out. I simply just said, all right, I'm going to do this the dumb way. I'm just going to build it from scratch, have it build all its assets, go through all of its resource stuff, and it was 1.4 times the speed of GCC. And you can see why our internal Android team really wanted to switch to Clang, because I don't know if you've ever heard of the kind of machines that it takes to actually build Android, the whole platform, but it's a lot of code. So just if you can improve your compile speed by 1.4, 1.5, 1.6 times, that's a huge productivity gain. But also there's great sanitizers that are built into Clang that the team loves, and actually the error messages are kind of cool. Although GCC is making massive, massive improvements there, so I wouldn't want to, but this is still, honestly, is huge for me. Now, there's a big thing about hard FP on ARM7. How many people have actually heard of this? How many people actually use it? Okay, all I can say is every time I've tried to use it, I've run into bugs. It's made I've run into things that don't work. It's a really, really, really hacky thing. And it's not used internally by the platform at all. And because of that, our tools team made the decision to eliminate it. So it is not an NDK R12. Basically, if you're making a whole bunch of calls to math libraries, this is where you'll actually get hit by this. And because what this is actually doing, it's not actually not using hardware floating point. It simply has to do with the way floating point parameters are passed in function calls. So if you look at the assembly that gets generated, it's a little more expensive. But the truth is, if function call overhead is your problem in your application, in your floating point intensive application, you've probably done something wrong. Like that's, hopefully you aren't actually making a call to do something extremely, extremely simple that you could just inline. And that's the hope. And most of the important math functions will get inlined. However, we know that there is some code that's going to lose performance because of this. But honestly, once we actually started looking at the problems with bugs that people were having and the fact that the platform team wasn't using it, and when the platform team doesn't use something on Android, it generally doesn't get nearly as well tested as it should be. So it's really, really important for us to do that. That's what's so great about what we've done with Clang, is that Clang is actually used, you're getting the exact same tool chain for almost the first time ever that's used to build the platform. And it's being very, very well maintained. It's also the same version of the tool chain that we're using inside Google data centers. And if you know the way we test stuff in data centers is we roll it out to 10% see what's going on, see if we hit any bugs, pull it back, change, do fixes. And so we actually get to take advantage of all the stuff that they're doing to make the data centers rock. So it's actually really, really good, I think, that we're actually all kind of united around making one compiler work really, really well. And not that GCC is dropping away. If you do need it, if your code doesn't compile, first of all, let us know if you have a problem compiling with Clang, and we'll try to fix it. And second of all, if you are, we are going to keep GCC around for a while. So it's not going away. We're just not updating to new versions. If you're expecting to get GCC 5, 4.9 is pretty much it. So one final thing is, if you really want high performance, definitely look at doing a 64-bit ABI. And really, I was actually not 100% sold on this, because you do end up using a little more memory. And that does, of course, mean you're using a little more memory bandwidth. But the extra registers that you get that the compiler can optimize around for 64-bit completely makes up for any memory inefficiencies it has almost all of the time. And we ran these benchmarks a lot. We've run a whole bunch of other benchmarks. In general, if you have something that's really, really performance sensitive, consider doing a 64-bit ABI. Consider, if it's not too big, just include it. Of course, you can include multiple ABIs in multiple libraries into any Android APK, or you can use multi-APK to distribute multiple different versions of your app. And again, it just works better. And the best thing about it is you already get hard floating point when you're running in ARMv8. Finally, x86 native. The x86 emulation that is in a bunch of Android devices that allow them to run ARM code is awesome. The fact that it performs this well on admittedly meaningless benchmarks is pretty good. But you can see, like with Whetstone, you can be giving up easily 2/3 of your performance by not having an x86 build. And so if you want to target devices like the Nexus Player and like the Zenfone, which are both pretty awesome devices, definitely consider actually doing a native x86 version. At least test it, because it really makes a huge difference in terms of battery life. Okay, so the Android runtime does a lot of things to make everything run fast. On Android LNM, it uses actually ahead-of-time compilation to bring the performance of bytecode much closer to native performance. And on N, of course, it uses a blend of just-in-time and ahead-of-time compilation. And once again, it deals much, much better with garbage. And what we're seeing with Art is that a lot of times you don't actually need to even go into native land. Again, if all you're concerned about is performance, Art is actually doing amazing, amazing stuff, and you don't have to worry about all of this kinds of thing. So it's complicated, as I said before. That means that it's a little more expensive to actually do a JNI call. And again, we have to do synchronization, and that's what's causing us to actually have these delays. So what's next? Basically, here are 2 links you can go to. One of them, of course, takes us into our NDK page. We actually have NDK docs online, which is amazing, and we're updating them. We have people who are actually assigned to this project to make it awesome. Secondly, we have great NDK samples, and we're putting more online all the time. So if there's anything you want that we don't have a sample for, an API that's not covered, let us know. We'll build samples.